EDX Decision 1, Linear Programming, Formulation and Graphical Solutions. Formulation of linear programming problems. Linear programming is used to solve practical and economical problems involving what are called constraints. For example, we may have restrictions on our time, or materials, or the number of workers or machines, etc. Real problems generally involve a number of constraints, and these are often written as linear inequalities. There is typically a quantity that we are trying to maximize or minimize, and this is called our objective function. For example, profit or waste we might want to minimize. And in doing so, this is called optimization. This objective function is used to define the quantity that we want to maximize or, in some cases, minimize. The first stage to a linear program is to formulate the linear program. This usually involves turning a very wordy statement into algebra to set up the constraint and set up the objective function. Linear programming can involve several variables. These could be quantities of different chocolates that need to be made, for example, or in our case, the number of types of boxes that we are going to look at. Determining the optimal values for these variables is the aim of the linear program. We will later look at solving linear programming in two variables using a graphical method. So here is our first linear program that we are going to look at. A company makes two types of box, each requiring the same amount of material. They both go through a folding machine and a stapling machine. Type A boxes require 4 seconds of folding and 6 seconds of stapling. Type B boxes require 2 seconds of folding and 7 seconds on the stapling machine. Each of the two machines is only available for 1 hour. So that's our restriction. There's a profit of 40p on each type A box and 30p on each type B box. Our aim is to find out how many of each type of box should we make in order to maximize the profit. So that's our linear programming in written form. We need to turn that into a mathematical form now. So the first thing I would recommend you do is to define your variables. So let variable x be the number of type A box that we make, and let y equal the number of type B box that we make. It's worth noting here that x is the number of type A and y is the number of type B. Don't just put x equals A, y equals B. That will be confusing. The other thing to note in this problem is that x and y will be integers because they are whole numbers of boxes. So always define your variables clearly. The next thing to look at is the objective. So what is our objective? Our objective is to maximize profit. So I'm going to call the profit P just to keep things simple. So we make 40 pence profit for every type A box, and we're going to make X of those boxes, so that will be 40 times X. We make 30 pence profit for every type B box. We're making Y of type B boxes, so that's going to be 30 times Y. And in total, that will be our profit. So that is our objective. Notice the equality. The profit will equal 40x plus 30y. However, we have what are called constraints. So the first constraint is on the folding machine. So I'll just call it fold machine just so we can keep tabs on things. So looking at the fold machine, to make a type A box takes 4 seconds on the fold machine. So we're going to make X of those boxes, Each box takes 4 seconds on the fold machine, so that will be 4x. The type B box takes 2 seconds on a fold machine. If we're making y of those boxes, that's going to be an extra 2y. So this is the total time in seconds that we need to fold the boxes. But we only have up to 1 hour of machine time available on the folding machine. So the total time folding boxes must be less than or equal to 1 hour. Make sure you don't mix up units here. The left hand side is in seconds, so we need the right hand side in seconds. So that's 3,600 seconds. So the total time folding boxes must be less than or equal to what is in effect 1 hour. There's also a constraint on the staple machine. Let's have a look at the staple machine now. It takes 6 seconds to staple a type A box. We're making X of those boxes, so that will be 6 times X. That's the amount of time we spend stapling type A boxes. It takes 7 seconds to staple a type B box. We're going to make Y of type B boxes, so that's an extra 7Y. That's the time spent stapling those boxes. So this is the total time stapling the boxes we're going to make, and the total time we spend stapling our boxes must not exceed the 1 hour again. We also have a couple of other what are called trivial constraints but need to be included. X, which is the number of boxes we make, must be at least 0. We can't have a maximum profit by, for example, making -4 boxes. X needs to be at least 0. And likewise, Y, the number of boxes of type B, must be at least 0 as well. And that has created our mathematical program. So there's our linear program ready for solving. It's worth noting that our constraint on folding, which was 4x plus 2y cannot exceed 3,600, has been simplified here by dividing by 2. It's still exactly the same constraint. 2x plus y is less than or equal to 1,800. It's the same constraint. Here we have a couple of new problems to think about. Sometimes students find it difficult to interpret these constraints. So X is the number of milk chocolates, Y is the number of dark chocolates, and our first problem here is there must be at least twice as many dark chocolates as milk chocolates. Now students often get this one the wrong way around, and the thing to notice is the number of dark chocolates is going to be more than the number of milk chocolates. So Y, which is the number of dark chocolates, if that's going to be a big number, is going to be twice X. So Y is the big number because it's twice as big as X. And there needs to be at least twice as many dark chocolates. So the number of dark chocolates can equal 2x, but it could also be more than 2x. So Y could be more than or equal to 2x. Likewise, we've got to be careful with this next problem. The number of dark chocolates must be less than 40% of the total number of chocolates. So the number of dark chocolates, that's Y, must be less than 40% of the total number of chocolates, and the total number of chocolates is going to be X plus Y. You could simplify this constraint afterwards, but the main thing is the structure of it. Y, the number of dark chocolates, is less than 40% of, and this bracket is the total number of chocolates, X plus Y. Some of the common errors with setting up the linear program: not defining variables X and Y clearly enough at the beginning, misunderstanding the appropriate inequality symbols, unclear use or a mixture of units, and not defining the objective function properly. In the next session we'll be looking at graphical solution using the vertex method.